Okay, so this is what happened. So people asked me a question about this exercise here. So the idea is that you have two separate groups of people that are surveying some roads somewhere, and one of them comes up with the road network that's labeled by these letters here, A, B, C, D, and so on. And the other team comes up with this adjacency matrix representation, right? So this is an adjacency matrix. So these stars represent ones, and these guys represent, like, empty spaces represent zeros. So this is our typical adjacency matrix. So it turns out, so I thought about this problem. I thought there was a unique assignment here of the vertices to the numbers. It turns out that there is no unique assignment. Okay, so you cannot, there's no unique correspondence of numbers to letters. Does not exist. Okay, there's the certain assignments you can eliminate, but there's no unique assignment. So we either need to change the wording of this problem to come up with a question like, what assignments are possible for vertex A, for example, or something like that, something simpler than what it is. As it stands right now, this problem cannot be solved as stated. Okay, so just ignore this problem. I will change it. I will be updating the entire sheet. I will take a second look at these problems. I will write the solutions to these ones and post them, right, to most of them. So which ones were more challenging? I think the first, so in the other section, one of the other sections, I did a problem that turned out to be very simple. Okay, so it was just random. So I thought that people would ask me a question and I'd start solving it and I'd do it in class, right? It turns out, so in one of the sections, we picked a very simple problem. It's just very straightforward. And in the other section, we picked a problem that it cannot be solved simply. It's just incorrect, this problem. Okay, there is no unique assignment. So I'll post the solutions to these problems. Just beware that there is a bug in this problem, 1, 2, 6. Other than that, which ones did you find challenging?
Mostly the like mathematical induction ones.
Oh, the math induction ones. Oh, okay. There are a couple of ones that are challenging there. Which ones did you get stuck in? Let's take a look.
I guess number 3 was like weird for me.
Okay,
Couldn't quite figure out how to like get back to the inductive hypothesis.
Okay, so let me find what number 3 is. We won't probably do it right now, but
yeah, it's okay. Like if you're gonna post the solutions, then we don't have to.
Oh, okay. Number 3, 213, right? Yeah, I'll post the solutions. Okay, so but why is this? What was your inductive hypothesis? Let's talk about this for a second. So the question is this: you have 3 to the n plus 7 to the n. So just to make sure everybody's on the same page, this is what you have. It looks like 3 to the n plus 7 to the n is divisible by 10. Is that the question?
Yeah, it's divisible by 10 whenever n is greater than or equal to 1 and an odd integer.
Okay, so take n to be 2k plus 1.
Yeah, that's right. Yeah.
And do induction on k, starting at 0. So k is 0. What is the base case? So 3 to the 1 plus 7. Do you see this? That the base case works.
Yeah,
so the base case checks out. What's the inductive step? So base case checks out because 3 to the 2 times 0 plus 1 plus 7, 2 times 0 plus 1 is 3 plus 7, that's 10, and that's 1 times 10. So it's a multiple of 10. So the base case checks out. Again, what's the inductive step? 3.
Yeah.
What am I checking? Suppose
we assume that 3 to 2k plus 1 plus 7 to the 2k plus 1. Wait, plus. Oh yeah, plus 1.
Let's assume that. So that's assume.
Yeah.
And what's here?
K plus 1.
Yeah. So is this what you tried and it didn't work out?
Yeah, I just like I wasn't sure how to get it into a format where
that's the problem. So so you have to make sure you find out why this is divisible by 10, right? So you have to simplify this. So what do you have? So here what you have is 2k plus 1 plus 2 here. Can you say that this is 9 times?
Yep.
Okay, and let me just rewrite it first. Again, plus plus 7 to the 2k plus 1 time plus 2, right? So can I rewrite this as 3 is 2k plus 1 times 9 plus 7 2k plus 1 times 49, right?
Right. Yep.
Is that right? So now I have to somehow make this divisible by 10. Do people see how this can be done? I see a couple of ways right now. Actually, no, I see just one way. Maybe you see more. Can I make this? Can I write this 9 as 10 minus 1 and this 49 as 50 minus 1? What will happen then? You'll have 10 times 3 to the 2k plus 1 minus 3 to the 2k plus 1, right? That's this piece. Do people see this?
Yeah.
Plus 50 times 7 to the k plus 1 minus 1 times 7 to the 2k plus 1. People agree?
Yep.
So now you have 10 times something plus 50 times something. Do you agree that something's divisible by 10? Minus 3 to the k plus 1 plus 7 to the 2k plus 1. Do people see this?
Yeah, I see it now.
All right, so this is a multiple of 10. It's 10 times something. And this is 10 times something by the inductive hypothesis.
All right.
People see this? So yeah, so this kind of question you can actually expect on the quiz, on the test. This actually, granted, I mean, it's, maybe you don't see it immediately, right? You do kind of have to work with it a little, just wrestle with it a little bit, but eventually it will come out. So it's not going to defy you forever, right? But this question, again, it wasn't this question, but since one of these questions just was incorrect. Which one was it? This one. Okay, so this one, again, somebody asked me, just as you asked me this question now about induction, somebody asked me this question in the other section, and I couldn't do it in time. Then when I thought about it, just now, actually, just before this class, it turns out you cannot solve this. There's just not a unique assignment. Actually, I found 2 assignments of vertices to these numbers that worked. And it's just not good, right? So I'll post the solutions to these problems. This question I will have to either rephrase or eliminate, but I guess I'm not going to eliminate. I'll just rephrase it because people have started working on it. It's still good exercise for the quiz. All right. Any other questions, real quick? We'll move on with the new material. And if we have time left, then I'll do more questions. All right. So
that question, you had 2 unique assignments. It wasn't that you couldn't make assignments. It was that you had 2 separate unique ones.
I had 2 assignments that worked.
Okay.
Not a unique assignment that worked. So have you tried? Anybody tried this question?
No, but
something in the chat.
I mean, it seems, I don't know. How I would approach is if at vertex 1, it's connected to 6 and 7, and then 7. You can check 7. 7's connected to 1, 5, and 6. So like you would just build it like that. So
yes, exactly. That's the approach. So this is how I start. So let's just get started and see where we get stuck. So so I have vertices of degree 2 here. These are vertices of degree 2, and then I have vertices of degree 3 here. Okay, right. I don't have a vertex of degree 4, right? So I have. Oops, why did I put a 4? Should be a vertex of degree 3. Okay, then I look at this adjacency matrix. And what happens in the adjacency matrix? Well, certainly this guy cannot be black, right? Because the black ones are the vertices of degree 2, right? Do people see this? And the purple ones are the vertices of degree 3. So vertex 1 must be black, right? There's no other way. Do people see this? Cannot be a purple one. Just help me out. Just tell me that people see it, because it has two entries here, two ones. It's connected to two vertices. That vertex 1 is connected to two others. So it must be one of the black vertices. Do people see it?
Yeah.
Cannot be a purple one. So similarly, vertex number 2 must be a purple one. There's no other way. So 2 must be this 2 cannot be C, for example. Cannot be C, for example, because C has degree 2 and so on. So when you do this kind of see which vertices can go with which ones, you can either color code them or whatever. So for example, vertex 1 can be either, so let me just write down a couple so that so 1 can be what? So vertex number 1 can be either A, C, or G. A, C, or G. And same thing, for example, vertex number 5, A, C, or G, etc. And then this vertex 2 can be one of these B, D, F, or E. Okay, so you write down all these possibilities that can happen. But then, okay, so there's once you write this down, you have nowhere near a unique assignment of anything. So then you have to check which vertices are connected to which vertices, which have connections to other vertices, and it quickly gets complicated. Okay, so let's move on. Now, let me ask you a question. So we're moving to linear algebra right now, and I want to ask you a question of what is a linear function, the way you know it. So we all know what a function is. It's a mapping from one set X to another set Y, very, very loosely put. It's just an association. It's a mapping. So element X gets mapped to something Y, like Y, element Y in Y. So please tell me, when do you call the function linear? So from calculus, what was a linear function?
It's an equation where it's only order 1, so it's just
Okay.
X, no exponential.
Yes, correct. So in calculus, so if you had something like Y equals 2X, for example, that was a linear function. You also call the function like this a linear function, which we won't call linear here. I'll give you a definition what we mean by linear here. Okay, how many people have taken linear algebra? How did you define a linear transformation there? Would this qualify, this purple line qualify as a linear transformation in linear algebra course? And why, if not? Okay, so let me define a linear transformation. So purple will not do, and the black one will do. Okay, so a transformation is linear. Let me copy this to have something. If two conditions are met, so we call T is linear. So T, F in calculus, and now we're T here stands for us for transformation. Transformation is a function. Just use this other word. T is linear. Okay, if when it acts on its input elements, you can add up the input elements and apply the transformation to the resulting sum. If what you get on the other side is the same as if you had applied T to U first, to the first element, and then to V, and then added those up, you'll get the same result. That's condition number 1 that we need satisfied. And you tell me if that's met, by the way, in your definition of a linear function. And the second one is that when you apply T to some constant multiple of an input element, then the result is the same as if you were to apply T to that input element, and then whatever comes out on the other side, multiply that by a constant C. If these two conditions are met, then T is called linear. That's our definition of what linear means. We'll see examples coming up. But first of all, ignoring the purple one here, for the black line, is this linear according to our definition? So our T of X, so here X acts on real numbers. By the way, the input and output for us, for these transformations that we'll be talking about, will be what we'll call linear spaces. For now, think of these as vectors. So T acts on vectors. So please remind me what a vector is before we check all of this. So let's leave some space here. Vector. How do we think of a vector? V. And let's stick with two-dimensional vectors here. So we have a couple of operations defined in vectors. So we have a vector, this vector 2, 1. We think of it as a quantity that has magnitude and direction. It starts at the origin and points in some direction. That's how we think about it from, like, I don't know, from high school physics or something. But it's really, we can identify each vector with a pair of points on the plane. Okay, its coordinates, the coordinates of its tip. And you have, let's say, another vector u. Let's say that one is 1, 3, for example. 1, 3. Okay. Okay, u, v, and u. What is v plus u? Or u plus v? How did
It's
you
just
add it?
1 plus 2.
Yeah,
At
so
the
you
top and
add
then-
up the coordinates. So what you have is v plus u is 2, 1 plus 1, 3, and you end up at, let's make that purple, the result, 3, 4. This vector here is 3, 4. The resulting vector is 3, 4. You add them up coordinate-wise. So that's the addition of vectors that you're used to. What does it mean to multiply a vector by a number? How do you think of a multiplication? Multiply a vector by a number.
You just multiply both elements.
Yeah, by that number, right? So it
Yeah.
amounts to stretching the vector. So if you multiply, I don't know, let's take u vector, I don't know, let's take v times 2. It's 2 times this vector 2, 1, right? You stretch it 2 times, as you told us, you multiply each component by 2. Let's make this 3 so that we don't confuse with other numbers. You multiply each component by 3. So 3 times 2 and 3 times 1. It's going to be 6, 1 vector. This 6, 1 vector is just taking this 2, 1 and stretching it 6 times. I'm sorry, stretching it 3 times in the same direction, the positive direction, this way. And wherever you end up, wherever the tip ends up, that's the resulting vector. Does this make sense to everybody? Everybody knows how to multiply a vector by a number, which corresponds to stretching of that vector, and adding 2 vectors to one another, right? Everybody remembers that. Now, our linear transformations will act on these vectors. So the linear transformation T will act on this space that is two-dimensional. This is our R2 that has all these vectors living in it. So this is, let's say, one of these vectors. Let's say this is another vector, like u. And when you apply T to this entire space, out comes another, it could be a 7-dimensional space, but let's say another R2. Okay, this vector, it means, is transformed as a result of T maybe here. T applied to V is some 2-dimensional vector here. Maybe T applied to U, let's say this is U, is some other vector this way. This is T applied to U. So what we have is we have a function that's applied to the entire plane here, and the output of it is another plane. And vectors get taken to other vectors in the output plane. This is the way to think of mappings here, of transformations. In calculus, you could plot these two. In calculus, your function f was from R to R. So you plotted both the input and output on the same plane. So this is a completely different plane. This is the input is here, the output is there, the y-axis. Okay, so anyway, back to this example. Is this function linear? So f does what? It takes x and multiplies it by 2. Out comes 2 times x. Why is it linear according to this definition? This is our definition. So f applied to, I don't know, let's take u and v. U and v here are some numbers. U plus v. Is it the same as f applied to u than f applied to v? Is it the same? Let's say u is 2 and this is 7. What is f of 2 plus 7? Is it equal to f of 2 plus f of 7? Is it? What's f of 2?
4.
What's f of 7?
14.
Okay, what's f of 2 plus 7?
18. Oh,
Okay.
sorry. Yeah, 2 plus 7. Yeah, 18.
Okay, 18. Is 18 equal to 4 plus 14? Yes. So it took, so here what I did is I took the sum and applied f to it. Here I applied f to the individually to the terms and then added those up. Either way I computed it, the result was the same, 18. This works for every pair. Same thing works if you multiply. Let's just try this. The second one. Let's do it. Is f 5 times u the same as 5 times f of u? Is it? Okay, so what is f? Let's take u equal to 4. Let's take u equal to 4. What is f times 5 times 4? What is that?
40.
So let's write, that's correct, but let's write it down. It's 2 times 5 times 4, right? Is it the same? Is it the same as 5 times 2 times 4? Is it the same? Is it clear what I'm writing down, or is just some symbols juggled around? Does it make sense to everybody? Anyone who doesn't make sense to, please ask. Is it clear what I'm doing? I'm just verifying these two properties, properties 1 and 2 for this particular function f. This checks that f is linear if those properties are satisfied. It's just, I'm just plugging in the numbers. Does this make sense? Okay. Anyway, this 2x is a linear function. So homework. According to our definition, homework. According to our definition, 2x plus 5 is not linear. Is not linear. In calculus, you called this a linear function. Is not linear. Why is that? Can somebody help me out? According to our definition of a linear function, a 0 must be mapped to a 0. Is it clear that 0, if t is linear, 0 maps to 0? Why? Why? Can I ask you why? Why does it follow from these two? A couple of ways of seeing this. Just apply t to S0, take c equal to 0. Then what's the argument here? For any u.
For any u times 0 is going to be 0.
0. And when you apply t to it, if this is to hold, so we're assuming that both of these properties hold. So when you apply t to 0, what comes out on the other side? 0 times something, right? Whatever the result is of transforming u to some other vector in the output space, right? It's some vector, could be 0, could be not 0, but whatever it is, it's 0 times that vector, which is 0. So 0 must transform to a 0 if, according to our definition. Everybody agree? It's a consequence of the definitions that we gave of what it means for a function of a transformation to be linear. Make sense? So if a transformation is linear, 0 must be transformed to a 0. And in this case, 2x plus 5, when x is 0, is transformed to a 5, not to a 0. Therefore, according to the definition, it's not going to be a 0. It's not going to be a linear function. So linear functions, according to our definitions, will go through this point, right? We'll go through this origin there. In fact, we'll actually think about linear transformation slightly differently than this. So I'll get to this in a minute. So let's continue. Just wanted to give you a definition of what it means for a transformation to be linear, and we'll see more examples of this as we go along. For now, we just want to do like our first step of what we'll do in linear algebra, which is start by solving systems of linear equations. I will give you an example where these things arise. Okay, so meanwhile, so here's another take on what it means. The same take, I guess what I wrote down is written down a little bit more neatly on this slide. So if you missed something about linear transformations, this would be a slide to look at. So what this slide really says is that you take T. This is T is the transformation. It takes a plane to a plane. It somehow transformed this. So we haven't yet talked about this, but stretching the plane in some direction and twisting it somehow so that parallel lines stay parallel and 0 gets transformed to a 0 will meet our definition of a linear transformation. Okay, so it turns out, so if the transformation is linear, then parallel lines will stay parallel. Okay, the angles may change, but parallel lines will stay parallel. Maybe we'll prove that later. It's a simple proof. But anyway, under this linear transformation T, this plane goes to this plane. And how about like individual vectors? Well, the result of applying T to twice V, this says, is the same as transforming V somewhere and then multiplying it 2 times. This is what this picture is trying to capture. Okay, so if you look at this, you will see that is happening. Does that make sense? And the second piece gives this explanation for the addition of 2 vectors. Right? Does that make sense? It's a definition of what it means for a transformation to be linear. It so turns out that the matrices, those grids of numbers that you're familiar with, correspond to linear transformations. In fact, every linear transformation from R2 to R2, say, in general, our transformations will be from Rn to Rm. Okay. The first example that we gave, the examples that we gave, were from R2 to R2. Okay. So again, these 2's can be some other integers. But anyway, this transformation T from a plane to a plane, it so happens that for each such transformation, there is a corresponding 2x2 matrix that looks something like this. And conversely, each 2x2 matrix that you can write down like this corresponds to a linear transformation. Okay, so we kind of need to talk about why that's the case. But first, let me give you an example of a transformation that can be given using a matrix that's linear. So you consume these chocolates and those nuts, and suppose you consume X grams of chocolate and X grams of nuts. And your body does this magic, this amazing machine that it is, and it transforms it into energy. Okay, so into that many carbs and that many fats. Okay. Well, how many carbs and how many fats? Well, it depends on how many chocolates and how much chocolate, how much nuts you eat, or whatever. So if each gram of chocolate gives you A carbohydrates, then you have that many carbohydrates from chocolates. And if each gram of nuts gives you B grams, B carbohydrates, then you get that many carbs from those nuts. For a total amount of carbs, this much. Same thing with the fat. This piece comes from chocolate, this piece comes from the nuts. So you get the idea. Now, the point I'm trying to make with this is just one of gazillions of examples that we could have given. The point is that this can be written down as a matrix times the vector of the nuts and chocolates that you can consume. So X amount of nuts and let's say X amount of chocolate and Y amount of nuts can be written down as a vector like this. And the machinery of, let's say, your body, of nature, that transformed this into carbs and fat can be given as a matrix, A, B, C, D. Now we know how to multiply matrices by vectors, just we have our mechanics of this multiplication, and here it is. Here are the mechanics. So help me multiply this. What comes out on the other side? AX plus BY, which is some number, C times X plus DY, which is some number. Okay, so for concrete, okay, so the people's bodies are given by these matrices A. So these are what transform food into energy. Okay, so every person may probably have like a different matrix associated with them that transforms this differently. Okay, every person consumes different amounts of like nuts and chocolates. So they have this different vector. Now, suppose I consume like, I don't know, like 5 nuts and 7 chocolates, let's say. Let's make this 5, 7. Okay, 5, 7. Okay, so if I knew that I consume that much, and if the body does this transformation according to like maybe some matrix like that, then you can compute how many carbs and how many, how much fat and how many carbs this chocolate and chocolates and nuts are transformed to. Does that make sense? So it's a transformation. So for example, this gets transformed to 7 times 1 plus 2 times 5. And this gets transformed to 15 plus 21, like this. So it's a concrete transformation with numbers. People get the idea. Okay, so maybe we spent too much time on this example, but the point I'm trying to make that this A times X equals B is what we'll be dealing with in the next couple of lectures. We're given some vector X, we're applying A to it, and out comes another vector B. Now let me ask you a little bit about what you already know. So I would read these slides that are posted there. The only thing is, for now, you can skip this page ranking stuff. That's meant to be an introduction to what we wanted to cover later, which is Google PageRank. I don't know if we'll get to it, but you can skip the web page ranking and the probabilities discussion. That's not going to be in any quiz. But let me ask you this: what will be on the quiz? What do you think about when people write down something like this? What does that even mean for X, Y, and Z to satisfy this? Think of it as a constraint. I mean, obviously, what this says is gives some kind of relationship between X, Y, and Z. X, Y, and Z cannot be completely arbitrary. You can have X be 22, Y be 27 million, and Z be 1, and still weigh those X, Y, and Z this way. So multiply the first one by 3, the second by 2, subtract 7 times Z, and get a 5. So obviously, not all triplets X, Y, Z satisfy this equation. So what do these triplets look like in the X, Y, Z three-dimensional space?
Is it a straight line or?
It's
no?
a
Yeah.
plane. It's a plane.
Oh, it's a
It's called
plane.
So let's look at this. What is 3x plus 2y equals 5? What is that? So let's say this is x, this is y, and maybe we should do it right here so that it's a neater picture. What is that? In two dimensions, it's easy to plot, right? So how do you plot this? First of all, what is this in 2 dimensions? What does it give? Is it a parabola?
It's a line.
It's a line. It's a straight line. How do we know? Well, let's plot it. So if we believe it's a line, all we need 2 points to plot it. So when x is 1 and y is 1, this is clearly satisfied, right? So this point is on that line. This is the 1, 1 point. 1, 1 point. What else is on this line? So if y is 0, okay, let's make x 0. Y is going to be 2.5. It's going to be 2.5, something like that. And you plot it. Okay. So this line has slope of 3/2, and it's a line. Okay, so it's a line in 2 dimensions. Okay, call it minus 3/2. This is the tangent of that angle. Anyway, it's a line. In the same way, if you tried, so let me see, I actually have this plotted in GeoGebra here. So that's the line that I just drew. You can either draw it by hand. That was simple enough. So, or you can give it to like your favorite software package that will draw it for you. This one, also, you can give this equation to your favorite software package that will draw a plane for you. That gives a plane in the 3-dimensional space. Okay. And if you had like one equation of 17 variables, it would give you what's called a hyperplane in the 18-dimensional space. So you're given, okay, in the 17-dimensional space, I'm sorry. Okay, so if you have 17 variables, it will be a hyperplane in the 17-dimensional space. It will have dimension 16 itself. Okay, just as 3 variables give a plane, like a flat 2-dimensional surface in 3 dimensions. And same thing, 2 variables here, x and y, give a line in 2 dimensions, a 1-dimensional surface in 2 dimensions. Okay, leaving that aside, let's continue. Now suppose you are given what's called a system of linear equations. What does it mean to solve a system of linear equations? So what is it? I have a concrete example here. Where's my concrete example? I have it here, or it's in the next line. So let's take a 2x2 example. I'll copy paste this. So let's see. This is the same that's on the slide. So let me use that. X minus 2y equals 1. 3x plus 2y is 11. So what does it mean to solve this system of equations?
find their point or points of intersection or like a line of intersection.
Okay, so that's the way we're used to from high school, right? So let's talk about that for a minute and then switch gears completely. So we'll adopt a completely different point of view of what it of viewing a system of linear equations. But let's stick with that point that you've just told us. Let me come back here and paste this system of linear equations. And let's actually solve it. Let's solve the way you told us. That's the first one. We want these two lines. Okay, we'll make one blue. This is the first equation, and the other, let's make it red. So let's draw the blue line. What does the blue line look like? When x is 1, y equals 0, this point is there. When y is 0, x is 1, we just have that. When y is 1, x is what? 1/2, right? Did I get this right?
When y is 1, x should be 1.
Sorry, one more time.
When y is 1, x should be 1.
When y is 1, x,
Oh, wait, it should be, when y
no,
is
no,
1,
this is
x should
correct.
be 2. Yeah. Or x should be 3, sorry, not 2, it should be 3. X should be 3
Oh.
when y is 1.
Okay, but anyway, you find these 2 points, you draw a line. So I just picked a different point. Maybe your point is actually better than what I picked, but your point is better. But I guess the one that I picked was I plugged in, again, yours is much better, but because it avoids fractions. But here, if y is 0, what is x? That's 1 point.
X is 1.
This point that I'm pointing, I don't
Yeah.
know if you can see it. When x is 0, what is y?
When x is 0, y is 1/2. So
Okay, minus
negative
1/2.
1/2.
Yeah.
Negative 1/2.
But anyway, you draw this line. Okay, with your 2 points, you would get exactly the same line. The point is, I just need 2 points. Okay, so then you have, let's draw the red line. What's the red line? So what's an obvious point if you plug in here? If you plug in x equals 3 and y equals 1. 3 and 1 at this point. How about x equals 1 and y equals 4? Does that work? Now I'm picking up easier points like you did. I could have picked the intersection with x and y, but whatever. The point is, I just want to draw these 2 lines. I want to find the solution to the system of equations, meaning I want to find the intersection of these 2 lines. And here it is. 3, 1 is the intersection, this point. 3, 1 is the intersection point. That's the solution to the system of equations. That's what you've suggested, right? This is the so-called row view of the system of equations. Now, let me just simply mention, why do we call this a row view? If somebody asked you to solve this system of equations, how would you solve it algebraically? Shouldn't have erased that. I want to erase the blue line. How would you solve this algebraically? You remember, so in school, like in high school, whatever, when you saw systems for the first time, you eliminated like one variable, plugged it into the other, right? Is that the way you did it? So actually, I don't know why I left the red line. Okay, so let's eliminate this variable. So let's eliminate x. So I'll go a little bit. So the first equation I'm not going to be changing, let's say. And what I'll do is 1 minus, 3 times 1 minus 1 times row 2, row 1. What's the result? So I'm leaving row 1 intact as it is. And row 2 has just become 3 times row 1 minus 1 times row 2. So I'm eliminating the variable x, right? What do I have? Do I have 8 times y equals 8? So let's draw this. This red line has just become this guy, which is y equals 1. or the same thing as 8y equals 8. And the blue line hasn't changed. It's still the same thing. Blue line, same thing. What's the intersection? Do you see that although I've rotated the red line, this algebraic manipulation of eliminating a variable corresponds to some kind of manipulation of this hyperplane. In this case, it just rotated this red line. We didn't do anything to the blue line yet. We could have rotated that one too. But the point is that we're doing it in such a way that the intersection point has not changed. The solution to this. Solution stays the same. This is what we'll be doing if you've seen Gaussian eliminations. That's what it does. It does these so-called allowed row manipulations. That corresponds geometrically to like rotating these planes around, these hyperplanes around, in such a way that the solution doesn't change. And when you do these row manipulations at the end, you end up with a system that looks much simpler. So the idea is for this to look simpler than this. Okay, granted, it's like a 2x2 case. It's not significantly simpler or anything, but at least we made one line parallel to one of the axes. I guess that's simpler. But anyway, you can simplify using these elimination of variables. You can simplify the entire system by eliminating these variables. So that geometrically that corresponds to rotating all these planes around. So at the end, it's easy to read the solution. For a human being to see solution, now in this case, it's easy to see in either case, or for a computer to read the solution. Now, this is what's called the row view of the system. And this is how you did in high school, right? Am I correct? Or if you remember, if you don't, that's fine. Now we're going to adopt so this is row view of the system. Now we're going to take what's called a column view of the same system. Column view. This will be our preferred new way of thinking about systems of linear equations. So again, let me rewrite this. And again, I'm going to give a geometric interpretation to what's happening. But this time, I'm going to write down the system of equations in matrix form. So do people agree that this system, let's copy paste this guy. This system, column view of this system, is A times X equals B. What is my A? What is my X? Whatever. So A is going to be, so help me write this down. A is going to be this matrix. X and Y will be the solution that I'm looking for. And the right-hand side is going to be 111. Now notice, now I'm going to give this a different interpretation. Now I'm going to draw these as vectors in a two-dimensional space. So this is going to be like a different, so here I'm going to be drawing like a completely different thing. Try to make it neat. Okay, it's not very neat, but this is what we, here's what I'm going to do. I'm going to view the columns of A as vectors in the two-dimensional space. Let me recolor them so that let's use a completely different set of colors so that we are not, okay, so 1, 3 is going to be the first column of A. Minus 2, 2 is going to be the second column of A. And X and Y will be the solution that I'm looking for. And what is that solution? That solution is how much do I have to stretch column vector 1, 3? How much do I have to stretch column vector minus 2, 2? So that when I add those two guys up, on the other side comes out exactly the right-hand side vector B. Okay, so now let's draw this. So our blue vector 1, 3 is here. 1, 3. That's my vector. That's column vector 1, 3. So I'm going to write it down now in columns. So there, I didn't write down anything in columns in the row picture. So I was dealing with the lines. So notice that although I have a two-dimensional case, the space here, this is a completely different R2. It's different from the R2 where I drew the lines. This is different. Let's draw the green guys, minus 2, 2, minus 2, 2. So that's this vector. So this is the second column of A, minus 2, 2 is column 2 of A. So how should I, what does it mean to multiply? What does it mean to multiply 1, 3, the blue vector, by y? So here I'm multiplying y times, okay, the green vector, or x times 1, 3. So x times 1, 3 means stretch it some number of times. Okay, I should stretch this some number of times, so that when you add those up, out comes, and I don't have enough space, but I think I can draw the vector 1, 11 here. Let's make it thick. This 1, 11 vector. This vector is the right-hand side vector. It's the right-hand side vector is 1, 11. That's B. So notice that if you told us how to, you know how to add vectors. So notice that if you stretch the blue vector 3 times, so 1, 3 times 3, and add to this 1 times 2 minus 2, what you get is exactly the black vector. Do people see that? Do people see that 1 times minus 2, 2, plus 3 times 1, 3 works out with the algebraic manipulation that you know of vectors, works out to exactly 1, 11. Just works out that way. And I've just drawn a geometric view of this same algebraic identity with vectors. I've just drawn them on the plane. So the point is this. I have to stretch the blue vector. This is the blue vector. I have to stretch it 3 times. If I do stretch that blue vector 3 times, and if I stretch the green vector 1 times, which means just 1 time stretch, just leave it alone. So if I stretch it 1 time and this guy 3 times, when I add them up, I get exactly the right-hand side vector 1, 11. So in this view of the system, I'm looking for the weights x and y, by which I weigh the columns of this transformation matrix A, so that when I add those columns up using these weights, which by the way is called the linear combination of the column vectors of A, I'm looking for some linear combination of the columns of A that gives me exactly the right-hand side vector B. That's what it means to solve the system of linear equations. And those two weights, that x and y, notice that happen to be exactly what we got as a solution in the row picture. The row picture intersected at points 3, 1, okay, which we found on the plane where the lines intersected, the usual view. The newer view, the column view, gives me those weights, x and y, like this, by which I weigh the columns of A to get the right-hand side vector B. Does that make sense? So now we'll stick with this view, with the column view. Okay, this will be our preferred view of the system of linear equations. Although starting next time, we'll look at a streamlined way of finding solutions to the system of linear equations. And there we'll still be manipulating rows. But when picturing the systems in our mind's eye, we prefer this column view. This will come in handy later also. When we talk about eigenvalues and eigenvectors, you'll have a nice background picture in your mind with those. And of course, we'll have all the algebra associated with it too, but we also need this geometric interpretation. Now, let me ask you this. Okay, and in the 3D, so we'll do a 3D example next time. Now, let me ask you this. How many solutions can a system of linear equations have? How many solutions can a system of linear equations have? So what does that mean? So let's take this 3x3 system. Each line, each row represents what? Again, help me out.
It represents a line, I guess, in the coordinate space.
Yeah, it represents a plane in the 3-dimensional space, right? So for example, the first two lines here may represent like here, this plane and this plane, okay? In general, two planes will intersect, like there will be an intersection of two planes. They don't have to be perpendicular. Let me draw it. There's a better picture on the next slide, but let me just draw it so that we all, so here's one plane. So let's say this is the green guy, the first equation. And here's the second equation comes in. I draw that plane that corresponds to the second equation. So again, I'm not Picasso, so you will forgive the quality of the drawing, but you'll see that two planes in general, okay, somehow intersect along some line. So one plane is there, another plane comes in, they intersect at a line like that. Okay, so that's the line of intersection. That's the first two. Then you have the third guy that comes in, the third plane, like somewhere here. In general, it will intersect this line of intersection of the first two planes at a single point. That single point will be a solution. Does that make sense? It's one way to view the solution to the system of linear equations. Three equations, three unknowns, a bunch of planes intersecting in space. I guess my question is, how many solutions can I have? Okay, clearly, the way I drew it, I can have one solution. So let me just show you a better picture. Okay, this is from the previous section. So let me erase what I have. So this gives me the first two planes, the first two planes. Okay, this one and this one somehow intersect at a line. Now, it's quite possible that these two planes are parallel to one another, or they coincide. But in general, you'll have some two planes will intersect at a line like that, like here. Then you have the third guy, the green guy comes in. That's the green guy, the one there. And the green guy will just cut through the two planes which intersected at a line, and you'll have a single intersection point, just a single intersection point. This is the situation when you have just exactly one solution. Now, please tell me, can I ever have like exactly 27 solutions to this system? No more, no less. There's no way, right? I either have just exactly one solution, or I'll have infinite solutions, or no solution at all. So when will I have like an infinite number of solutions?
You'll have an infinite number of solutions when there's a line of intersection.
Yeah, for example, when the third plane comes in and this line of the intersection of the first two happens to be right on that third plane, like live inside that plane, that's an infinite number of solutions. Instead of one solution like that, I now have an infinite solutions, this entire line. Or I can have all three planes just be the same, right? Just coincide. All three planes be the same plane, give the same plane. So these equations may be multiples one another, in which case they will give me the same plane. Okay, so or you can have two planes coincide and the third plane just cuts through somehow, and again gives a line like that of solutions, again infinite solutions. Or I can have no solutions at all. Like one plane is separated from another plane, it's like parallel like this, and the third plane does whatever it wants to do. All three of them will never have a solution, right? If two planes are parallel and separated with one another, from one another. Okay, does that make sense, right? So because later we'll want to see what, again, this is just a preview of what's to come. Again, next time we'll have a streamlined way of solving this system of linear equations. We'll talk about what's called Gaussian elimination, Gauss-Jordan elimination. It's still called Gaussian elimination, although we now know that, for example, the Chinese mathematicians had this method long before, but still called Gaussian elimination. So we'll discuss that algorithm next time. And then we'll move on to other topics like eigenvalues and eigenvectors. All right, any questions about any of this? Okay, so this can be an interesting topic. So this one is from the previous section. Now we have a couple of minutes left. Again, going back, so is it clear now what we're doing for the exam? So when is the exam again, please? And
this Friday.
Spend a couple of minutes on that.
Yeah.
So yeah, so the exam is on Friday. Now you have one recitation which will be devoted to the review for the exam. I will post the solutions to most of the problems that are posted there. By tomorrow morning, I will add I want to add like 5 questions to it. Like to the graph section and to the induction piece section. And once we add those, once I add those problems, I'll add solutions to and post them. The problem I told you about turns out doesn't have a unique solution. I will either eliminate this problem or maybe leave it and change the wording so that you can, it's clear what the solution is, and I'll write up some shorthand of that solution so it's clear what's happening. And I think you should be good to go, right? So now what to expect in the exam, you'll probably have about 10 questions, roughly 6 minutes. So so when I started doing this in the other section, so it went over 6 minutes, right? Before I realized that there is no good solution to this. So you don't want to deal with that kind of stuff on the exam. So yes, you may have a couple of questions that will take you longer than 6 minutes to solve, like twice as long maybe, but others will be quicker.
I have a question. It's about linear algebra. It's conceptual. So if it was in a 3D space, if you had a system of equations that were like 3x plus 2y is equal to 4, it would be the full plane, right? A straight plane. So I guess in a 4D area where you have 3x plus 2y plus 4z is equal to 17. Would that be in the 4-dimensional space? It would be like straight 3-dimensional
yes. Yeah, that's yes. If you have 4 equations, if you have x, y, z, and u or something like that in 4 dimensions. In general, that will give you a 3-dimensional, what's called hyperplane in 4 dimensions. So if we were able to imagine 4 dimensions, that would look exactly like, well, again, this is speculative, but like planes in the 3-dimensional space. They live inside just as these planes that we saw in these pictures live inside the 3-dimensional space that we can imagine. In exactly the same way, in the 4-dimensional space, those 3-dimensional objects live and intersect somehow.
Yeah.
But those can intersect along planes or lines or again,
whole 3-dimensional.
Yeah, the thing is, in the 4-dimensional space, the whole 3-dimensional spaces can be parallel in the sense to one another. They may have no intersection at all.
Yeah.
Which is in our minds is impossible to imagine as a picture. But algebraically, you can write this down, right?
Yeah.
And that's why we use algebra, so we can deal with the problems that we cannot picture after a certain point.
Thank you.
Yeah, but so yeah, so we'll talk more about this. Now, what else is happening here? All right. So, any other questions? I think that's basically it. Okay. So, as it comes to the exam,
That's really quick. I don't know if you mentioned this, but like, how many questions is the midterm going to be roughly?
Yeah. So this is what I was saying. So roughly, so if you have 10 questions, right? So you have an hour and a half. That's like 9-ish minutes. Okay. So let's say 6 minutes. Okay, so they will be designed, if there are 10 questions, they will be designed to be 6 minutes each. So roughly you could complete it in 1 hour, but you really have an hour and 20 minutes. Right. And most people will take up an hour and a half, right? So because I'll be here anyway, and you'll be like, okay, so I have an hour and a half. And okay, so you will be given that hour and a half if you need it, right? So it may be that so I don't know how many questions there will be exactly, but it will be fair so that you will fit in that time frame, and you'll have some time left over actually when you complete it. Right, so it will be fair time-wise in that regard. Although it will be a little bit more strained than if we were to do this in the classroom with no cheat sheets or just one single cheat sheet. So the way we're doing this now, it's like an open book exam, right? So people are Googling all over the place. So there you won't. So that implies that you won't have questions like, as we talked last time, is this function a big O of another function? No, because you can Google it and just get the answer like right away. So that's not a question for the exam. The question will be, you will have big O questions, but ones that involve explanations. So what is the smallest c for which this function is big O of that function when k is 17 or something like that? Those kinds of questions, and you'll have to kind of work it out. You'll have questions on graphs. You'll have questions on induction. So all of these, you have to write down the explanations right by hand, right?
Is it Zoom proctored, like with the camera on?
Yeah, so it's, okay, we're not using Proctorio, right? So there's no Proctorio, but here's what will happen. I will be asking people to turn the webcams on, but half of you will not turn the webcams on. So then what would I do? Will I start chasing people around, like to turn the way you start yelling or something? I mean, I don't know what would I do, right? So I will ask you to turn the webcams on. Those of you who don't mind and turn it on, that would be good. But I'll be doing my own thing. You'll be doing your own thing, right? Yeah, so, but the point is, like, we'll all fit into this time frame. The exam begins and ends. So it begins at the start of the lecture, ends at the end of the lecture. You have an hour and a half roughly, except for those people who have DRS accommodations, you'll get extra time. Other than that, we'll just, it's just the time frame is the main constraint. Right?
Professor, I have a question for you.
Yeah.
I assume the format's going to be the same as you do when you take the quizzes, where we're going to be writing stuff out and then submitting a picture of stuff to upload spot.
Yes, exactly the same. So you just write it by hand, take a picture, will be a separate upload area, just upload it there. Same thing. The workflow is the same. What else? I think that's it. So you will have a quiz this recitation though, right? Because you haven't had one on Dijkstra's and Euler's formula and any of that. So that's good practice.
Sweet.
So you're essentially preparing for the exam as you're preparing for the quiz. It's just part of your midterm preparation. All the quiz questions, all the quiz answers are posted on Canvas. You have them there. And then I'll post the solutions to these questions as well. Okay. All right. Any other questions? Okay. So I'll see you guys on Friday.